So far, we've talked about limits graphically. So we've looked at graphs and computed limits. We've used tables of values and computed limits numerically. And now we're aiming to find limits algebraically, which is going to give us a way to find exact values for limits. And remembering that our long-term goal is to find slopes of tangent lines, we need to be able to find exact values of limits in order to do that. So before we start really kind of jumping into the algebraic way of understanding limits, we need to understand the limit laws, which will eventually allow us to get to these like real algebraic limits. These limit laws underlie a lot of the properties we're going to talk about in calculus, but you're not necessarily going to notice they're there. So they're super important. They kind of hide in the background. They're a little shy sometimes, but they actually really live there. So limit laws give us a way to break apart limits. They kind of behave like you might expect that they should, which is good. So we're going to look at these limit laws, and I'll give you a few examples here, and then we'll do a lot more examples on the next page. So we have two functions, f of x and g of x, and we know something about their limits as x approaches some particular number. And so the limit laws give me a way to deal with sums or differences or products or quotients of these two functions and their corresponding limits. So let's maybe suppose we have some function so that we know the limit as x approaches 2 of f of x is 5, and the limit as x approaches 2 of g of x is 1. So this is information that we've been given, and let's actually make that a -1 just for fun. So this is information we already know about these two functions, and now we're going to use this information to look at what happens with combinations of f and g. So if we look at these first two properties say if I add f and g together and then I take their limit, well, that's the same thing as just taking their limits and then adding those together. So it doesn't really matter which order we do the addition in and the limit in. We can do the limit first, or we can do the addition first, and it doesn't matter. So like property 1 here would tell us that if I look at the limit as x approaches 2 of f plus g of x, then this is the limit as x approaches 2 of f of x plus the limit as x approaches 2 of g of x. And this might have been what you tried had I not told you this property worked, but this is a true property of limits. So this first piece is 5. The second piece is the -1. So we have 5 plus -1, which is +4, not -4. Okay, same thing happens if I replace the addition with subtraction. That's what that second property says. So I can just change all these addition signs with subtraction signs. I'm being lazy here. So 5 minus -1 will give me 6. So if I add or subtract between limits or between two functions, then I can break that apart between two limits where I add or subtract. Same thing happens with multiplication. If I multiply two functions, then I can multiply the limits. So I have the limit as x approaches 2 of f times g of x. That's the same as the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. You're noticing these problems are going to be tedious, and they really will be. It will be a lot of rewriting. And so the f of x piece is 5, the g of x piece is -1, so we get -5 out here. Okay. We can do division as well. With division, the thing that we have to be careful about is that the denominator cannot be 0, or the limit of the denominator cannot be 0. If that limit of the denominator is 0, then the limit laws don't tell us anything. And actually, that's going to be the case that we're going to spend like 3 class days working on, is what happens when the denominator's limit is 0. So we're not going to talk about that for this class period, but we'll worry about that later. But like in this example here, we would have like a limit as x approaches 2 of f of x over g of x. Well, I can break that into the division of two limits. And so this would be 5 over -1, which is still -1, no, or which is still -5. Can't do simple math here. Remembering with all of these problems that the x values are approaching the same number. All of these limit laws make that distinction there. And then this property number 4, which I had skipped over, this tells us if that I multiply a constant by a function, I can pull the constant out of the limit. This is a property that we'll use a lot throughout the semester without remembering that it comes from a limit law. So if I do like the limit as x approaches 2 of 8 f of x, I can take that 8 outside of the limit. So I have 8 limit as x approaches 2 f of x. And then this guy was 5. So this is 8 times 5 or 40. Okay. So hopefully those all behave kind of in a way that you might expect. Let me skip down to these last two, and then I'll come back to those first two. So if I have a function raised to a power, then I can rewrite this as a limit as x approaches a, that limit raised to the power. So if I use that same example I had before, if I look at limit of f of x approaching, or as x approaches 2 of f of x, if I square that function f of x, then this property tells me I can pull that square out. So I can compute the limit first and then I can square. The limit was 5 from before, so we get 5 squared or 25. And then that last property says I can do the same thing with roots. So if this was like a square root or something like that, I can move the square root outside of the limit. So these last two properties are just kind of similar ideas. Now properties 6 and 7, I have to fill back in. I didn't give you the final answer here. So property 6 is looking at constants. So C is a constant. So this would be something like the limit as x approaches 2 of the number 3. It's asking what's happening here. Well, what's going to end up happening here is we just get that number 3 out. Whatever the constant is, it just gets spit back. This number here didn't matter. So if this was like a limit as x approaches 10 of 3, I still just get that constant 3 back. You should think about graphically why this makes sense. Oh, we're not always going to get 3 back. We'll always get C back. Think graphically about why this makes sense, and we'll explain it in class. This next one is the limit as x approaches a of x. X's are variable. So we could think maybe limit as x approaches 2 of x. In this case, we're just going to plug, we're going to plug the 2 in for the x and we'll get the 2 out. So in general, we'll just get a out. So like limit as x approaches 4 of x, just plug that 4 in and we get 4 out. Once again, we'll talk about why that's the case in class. All of these properties hold for left or right-hand limits. If I replaced all of these limits with a right-hand limit, same properties hold. Same if I did left-hand limits. Okay, on the next page, we'll do a few examples of these.